Good evening, everyone, and welcome to the Brian Crombie Radio Hour on Saga 960. So Monday, something is happening that's incredibly unusual and happens very rarely, and we've got a real expert tonight to tell us a little about it. I want to introduce you to Jason Harlow. Jason is a teaching stream professor in the physics department at the University of Toronto. He's got a PhD in astronomy and astrophysics. A PhD in astronomy and astrophysics. This guy's like smart, like really smart. And he's from the university, the Pennsylvania State University, and he has a lifelong interest in telescopes and stargazing. In 1991, Jason traveled to Costa Rica to view a total solar eclipse. I think there was a song about that. You're so vain. You had to go up to New Brunswick or Nova Scotia to see the total eclipse of the sun. That's not you, of course, but there is a song about that, isn't there? And so this is the second time you're going to be seeing a solar eclipse.
Yes. Yeah. Hopefully.
Jason, welcome to the show.
Yeah, thanks.
Why do you say hopefully? Because we need good weather?
Yes, exactly. It could be cloudy. That's the whole issue, is that it depends on the weather, and we're not quite sure, right? But if it's clear, it'll be pretty amazing.
And I'm told that we should go to Niagara Falls.
Right. So Toronto and Mississauga, unfortunately, will not get a total solar eclipse. So there's going to be a solar eclipse on Monday all over North America, which is called a partial solar eclipse. So basically, yeah, when the moon is orbiting around the Earth once a month, and the Earth orbits the sun once a year. And so every time the moon passes between the Earth and the sun, sometimes the shadow could fall right on the Earth. And since the orbits aren't aligned quite exactly, this is pretty rare, but it will be happening, like I say, on Monday. And in this case, there's actually a total solar eclipse, which is very rare. It's
how rare?
Well, it sort of depends. If you're willing to travel, and you can go anywhere on the Earth, then I think on average there's a total solar eclipse about every year and a half. However, if you don't travel, like if you see a total solar eclipse in one specific place, the odds of that happening in the same place again, like that won't happen on average for another 375 years. So the ability, because the idea is that the actual path of the shadow of the moon, where it blocks out the sun completely, is quite narrow. It's about 180 kilometers wide. And so if you can go to that path of totality, as they say, then you can see them more than once in a lifetime. And like I say, back in 1991, I got on a plane and traveled to Costa Rica. And so I guess I'm one of the eclipse chasers, but there's a lot of people who chase eclipses all over the world. And in fact, I know of a lot of people who are actually traveling to Mexico or there right now to see the eclipse on Monday, because in Mexico it's less likely to be cloudy. And so this eclipse on Monday starts in Mexico, goes straight over to the United States through Texas and Missouri, and ends up going straight over Buffalo. And it gets the chances of it being cloudy get higher and higher as you go towards, it ends up in Newfoundland, actually. So partly what eclipse chasers are doing are going to places where they think it won't be cloudy.
So you're saying that it happens, reasonably frequently somewhere on the Earth, but once every 350 or so years in the same place on Earth. Why is it so unique then? Is it just because it's rare, or is there something else about it's almost got a mystical or spiritual aspect to it, doesn't it?
Yeah, definitely. So I guess maybe I'll tell you about my experience. So yeah, we traveled up to a cliff sort of overlooking the ocean, and so the main thing about a partial solar eclipse is you really need eye protection to view it. And so back then, what I had was a piece of welding glass that I'd bought at the hardware store. So for about an hour and a half before the total solar eclipse, the sun or some part of the disk of the sun is still visible. And that's incredibly dangerous for your eyes. You should never look right at the sun without eye protection. And these days, you can go and get eclipse glasses from lots of great websites around, solar eclipse glasses, as they're called. So you definitely need eye protection. And what you see is the sun, you look up at the sun, which looks like a circle through the glasses. You can't see anything except you see the sun. And and then there's a little cookie cutter shape of the moon kind of blocking it out. And that grows and grows and grows over the hour and a half until it's almost completely blocking the sun. And the other thing that happens while this is happening is that you start to feel it cool down. And if you take off the eclipse glasses to look around you, you notice that the light has changed kind of weird. And so it's like maybe like twilight or something, even though the sun is above you. And then in a total solar eclipse, what happens is that suddenly it just gets dark like night. And you can, at that point, you can take off the eclipse glasses because it's night, and you look around and it seems like night. You look up and you see something that I don't even know how to describe. It's something so alien. Where the sun was just a few minutes ago, instead is replaced by this just like a black hole in the sky, surrounded by these kind of brushes of, I don't know what, a little bit of shimmering light. It's actually the corona of the sun, but just something you have never seen before. And the other thing you see is the stars have come out. And so this was the summer that I was in Costa Rica, and I saw all the winter constellations because I guess in the orbit of the Earth, you're looking in the wrong way, right? You're not looking at the normal nighttime sky. You're looking at the nighttime sky from 6 months ago. So I was able to see Orion and Pegasus, and Gemini, and I saw a line of planets, these sort of brighter stars, almost forming a line that was centered on the sun, and that included Mercury and Venus and Mars and Jupiter, all sort of aligned there. So it was really beautiful. And then on the horizon, you could sort of see this almost like a twilight or something. So it wasn't completely dark, but it was pretty dark, certainly dark enough for the stars. But then it started getting colder and colder. And I think something deep inside me was very afraid during this time. And I started to just feel, I don't know, anxiety or something. And then when the sun came back, there was this collective relief of the entire crowd. Everyone cheered and clapped. And it felt so good that the sun was back. And it really affected the wildlife as well. So we never saw a bird for the rest of the day. This was at about 2 o'clock in the afternoon. Never saw another bird. And what we did see were insects. The insects, something about them had that told them, okay, it's night. So they all came out, and maybe about 2 or 3 hours later, it was quite hot again because it was summer in Costa Rica, and it killed so many dragonflies. There were the ground was just covered with dead dragonflies. You couldn't even walk because I guess they're not able to handle that kind of heat. So it really messed with the wildlife as well.
So it was quite the experience, and you recommend that the rest of us give it a shot.
I would recommend it. Yeah, it's worth the drive. Like I say, if it's clear, it's definitely worth the drive to Hamilton. So Toronto and Mississauga will miss it. It'll get quite dark, but you should never look at the sun during a partial solar eclipse. So you won't be able to look at it from Toronto or Mississauga unless you have your eclipse glasses, and it won't really be that same experience. So I think Hamilton, it starts right around Burlington. There's a short eclipse, and the closer you get to Buffalo, the longer the duration of the eclipse. So it's about a minute in Hamilton. And way down in Buffalo, or Fort Erie is where I'm going to drive actually, should be about 3 minutes of totality down there.
And this is Monday, April the 8th at around
Yep.
what time?
It's going to be, so the partial eclipse starts at 2 p.m. The total eclipse starts at 3:15 or 3:18, depending on exactly where you are. So 3:15 in the afternoon. That's where you want to be in Hamilton or a little south of there.
And some people are worried about kids getting out of school and stuff.
Yeah, well, it's a PA day. And so I guess, yeah, there's the opportunity there if you can hop on a GO train or something and go down to Hamilton. I know there's a lot of events being planned. McMaster University has a big event at their stadium planned. But yeah, I guess the worry just is that you really kind of need these like some solar eclipse glasses, and there's a lot of, like, I think in Hamilton, they're giving away free glasses and stuff. So it isn't.
Sunglasses don't work.
No. Sunglasses don't work. You shouldn't look through a DVD. You really need some proper eye protection if you're going to look at a partial solar eclipse. And like I say, for the whole hour and a half before the total solar eclipse, there's really going to be a temptation to look up at the sun getting covered by the moon. But until it's completely covered, this is another issue. So even if the disk of the sun is 99% covered by the moon, the little remaining disk of the sun is such a concentrated intensity that it can still damage your eyes. That's important to remember is that
1% of the sun can damage
because
your eyes.
yeah, it can. It's not exactly the total light that's coming from the sun, it's the concentration. That surface of the sun has just such a high intensity that when you focus it down onto your retina, it can actually burn a tiny little hole in your retina and cause permanent eye damage. So I mean, if you take a quick glance or something, I think we've all done it. You regret it right away. It's never good to look at the sun, and that's just the same for at any time. But during a partial eclipse, I think there's more of a temptation to look up there and check it out, especially when it seems to be getting a little dark. But you should not do it until it really becomes dark, and then you don't.
So, a former president of the United States, Donald Trump, said he looked at the sun during an eclipse and he was fine. So, did he have something special or supernatural or what?
No, it's just stupid. You shouldn't do it.
We're going to take a break for some messages after that profound comment and come back in just 2 minutes with Jason talking a little bit more about the sun and parts of the sun and how often this happens and why he got so interested in this topic. Stay with us, everyone. Back in 2 minutes. Welcome back, everyone, to the Brian Crombie Radio Hour on Saga 960, Monday, April the 8th at around 3:18 p.m. In around our area in Mississauga and Toronto. There will be a partial eclipse of the sun, southern Ontario down near Hamilton, Niagara Falls, Fort Erie. There's going to be a full eclipse of the sun. And we've got with us tonight to tell us a little bit about it, Jason Harlow, who is a teaching stream professor in the physics department at the University of Toronto. He's got a PhD in astronomy and astrophysics from Pennsylvania State University. He's got a lifelong interest in telescopes and stargazing. And in 1991, Jason traveled to Costa Rica to view a total eclipse of the sun. So this will be his second time seeing one. Jason, can I ask you a couple of questions about our first couple of minutes? You said that the sun's corona is still visible. What's the sun's corona? Can you tell us a little bit about the different parts? Because I've been told that in addition to the corona, another interesting thing is that there's flares that come out that can be seen during an eclipse that can't be seen the rest of the time. Maybe tell us a little bit about what interesting things can be seen during an eclipse that you might not see at other times.
Yeah, okay. So yeah, when there's an eclipse, so the main part of the sun that emits all the light is called the photosphere. That's the I guess the place where most of the light suddenly leaves and starts traveling through empty space, and it's a big sphere, pretty smooth sphere. But upon the photosphere, there is a lot of turbulence. So this is it's called a plasma. So it's a gas that is that's very hot and very ionized, and there's a lot of electric and magnetic fields. And what happens with these magnetic fields is they can cause parts of the hot gases there to shoot up off the surface. And it's almost like the surface is boiling a bit, but there are convection currents of the plasma. And sometimes, if the magnetic field is very strong, it can either cause like it's called a sunspot. So you can actually see an area where it's a little darker, but then above a sunspot, you'll often get these flares that leave the surface of the sun. It can go very far, in fact. Now the corona, as you asked about, is like an outer atmosphere of the sun. So it's just a region of transparent, very hot gas that surrounds the sun and that is affected by these flares and the magnetic field. But it does emit a bit of its own light, which you'd never see normally, except you can see it during a total solar eclipse. So the other interesting thing about eclipses is that the sun is actually much, much bigger than the moon. It's about 400 times the size of the moon. But as seen from Earth, the sun is also just about exactly 400 times farther away from the Earth than the moon. So this is an amazingly lucky coincidence that distance is the same factor greater than the size difference. So when you look at it, the angular size that the moon and the sun take up in the sky are almost about the same. It's about 1 degree of angular size. And so So they look about the same size. And so what happens when the moon covers the sun in a total solar eclipse is it just covers the sun. And so what you see around the edges of the moon is the corona. And it's something that you never get another chance to see. And so, in fact, even astronomers are interested in solar eclipses because you get a chance there to block out the photosphere and all that extremely bright light and see this outer atmosphere of the sun. And it's very beautiful. And then sometimes, although you need a telescope to see it, you can actually see flares of the sun around the moon. But I didn't see that because I didn't have a telescope out at that time. I was just looking with my eyes. And I think for me, that's what I'm going to do on Monday as well. I just want to see it, and experience the feeling of it. And I don't really want to be fussing around with my telescope at that time. So.
When I read this thing about the 400,
Yeah.
400 times the size and 400 times farther away, you got to wonder about the coincidence of that. Like, is there some mathematical, law that says this had to happen, or was it pure chance, or was it some intelligent God? Like, how does that happen?
It's just pure chance. I mean, the fact that Earth has a moon, a big moon like that, does have effects. Like, for example, it creates the tides in the ocean, and a lot of people believe that life developed in tidal plains near the ocean between the land and on the shore. So the moon is very important to Earth and stabilizes it as well. So it stabilizes this rotation so that the seasons are pretty stable over the thousands of years. But yeah, the fact that it would be just the right size at just the right distance is purely a coincidence. And I think we're just lucky to have that.
Explain that. How does the moon stabilize the Earth?
Well, the gravity from the moon pulls on the Earth and causes, I guess the bulge of the equator of the Earth to actually precess like a top. And so without a moon, like for example Mars or something, what can happen is just chaotically the rotation axis of a planet can change around, and it can dramatically change the seasons over many millions of years. And that doesn't happen if you're locked into this gravity pull sort of precession dance with a satellite. So it's a lucky thing, but
So that's
it's
interesting. So you're saying Mars does not have a moon that stabilizes it,
not a big moon. Yeah, that's right.
and so that it can change its rotational.
Its rotation axis can change, which can dramatically change the seasons on places on Mars's surface. So
But it wouldn't be every year; it'd be over a million years.
yeah.
So it wouldn't be like all of a sudden be summer here.
No, but if life is trying to evolve and it needs some sort of steady environment over millions of years, which it might, I don't really know how life starts on the planet, but that's harder to do if you don't have a nice stable orbit, which you get if you have a big satellite. So Mars does have a couple of moons, but they're so small they don't have an effect on its rotation.
Do all planets have moons?
I guess Mercury and Venus don't have moons, but I think all the other ones do have some. Even Pluto has a pretty big moon as well. So
And so do Mercury and Venus have unstable rotation?
yes. Yeah, well, actually, what happens with Mercury and Venus is that they're more affected, especially Mercury is more affected by the gravitational pull of the sun. Since it's so close to the sun, there's tidal effects from the solar gravity there, which actually have really slowed down Mercury's rotation to almost be locked with its orbit. So it has a very, very long day compared to its orbit.
Really, that's interesting. So let's come back to some of the other things that you mentioned. You mentioned something really surprising. You said that we're looking at the sky from 6 months ago. What the heck do you mean by that?
Well, what I mean, yeah. So what I mean is that I'm very used to looking at the stars. And so in the summer, I go out and I see the summer triangle, and I sometimes see Leo and things. And so I get used to seeing those when I see Arcturus coming up and my friendly, cottage kind of summer stars. And then in the winter, when it's really cold out, you get the longer nights, but I go outside and I see a different bunch of constellations. I see Orion, I see Auriga and the Pleiades and all these beautiful. It's actually I prefer the winter constellations. There's more variety, and Orion is so beautiful, and you see just a nicer array of stars. But it's very cold, and so there's that. And so And the reason for that is because as the Earth is orbiting around the sun, it's daytime in one direction, and so you don't see the stars, and it's nighttime in the other direction. And you go 6 months later, well, those directions have flipped, and so that's why we see a different part of the actual sky. So what happened when you what happens what will happen when you see this total solar eclipse is that the stars that you see overhead, so they were already there, by the way. That's the weird thing, is that during the day, the stars are there. You just can't see them. The reason you can't see them is because the sky is blue. And the sky is blue because it's got so much scattered sunlight that it just blocks out the stars. So if you block the sun, then the sky becomes transparent again, and you can suddenly see out. And what you'll see is, if you think of it, you'll see the wrong direction. You'll be looking towards the daytime direction. And so you'll see all those stars you remember from 6 months ago. And so it's just different constellations. And that was a surprise to me, actually, when I first saw a total solar eclipse. I was like, whoa.
You said that everyone cheered when the sun came back out. Is that
Yes.
because people were worried the sun was going to be gone forever? Like, why did they cheer when the sun came back out?
Okay, so like I say, I'm an astronomer. I have a PhD in this stuff. I absolutely knew the sun was coming back. I knew to the second how long the totality would last, but I don't know. I just felt worried. It's because, because the sun is so important. And it's the provider of life and of heat. And so if you're there and the sun goes away and it's replaced with something alien you've never seen before, I don't know. It's something very deep in my brain. My amygdala or something was nervous. I guess it's like I kind of felt panicky a little, and I was just so happy, deep down so happy when the sun returned. And everyone sort of, I think, shared that feeling. So I mean, you can imagine in ancient days when people didn't know that there was an eclipse coming, and for this to suddenly happen, the amount of panic and fear that it must have caused must have been immense, because the sun is gone. And you think, what's going to happen now? Are we all just going to freeze and there won't be, everything will die and nothing will come back? But then it does come back, and like I say, it's a nice feeling. So there's something
Are there any
primal about it.
stories of that from history of eclipses and what it might have done to cause fear?
Yeah, well, yeah, there's lots of stories of people. Eclipses have made it into literature for many years. There's also eclipse chasers, people looking, and astronomers going around in boats to try to find where eclipses are going to be, and see, not only see the corona, but another interesting thing you can see during a solar eclipse is the stars that are behind. They're in a certain constellation and a position, but right near the sun itself, the positions of the stars are changed just a tiny bit. And the reason for that is because the light that travels past the sun actually bends with the gravity of the sun. And this was a prediction of Einstein's theory of general relativity, which came out in 1915. And at that time, it was just a theory, but eclipse chasers were going around and trying to find a clearer day where they could actually observe this. And it was observed, I believe, in the late teens, 1918 or so, to see that general relativity was correct, Einstein was correct, and that light can bend in a gravitational field. So that's another scientific reason for this.
How does light get impacted by gravity?
Well, that's the theory of general relativity, which is that what gravity is actually a bending of space and time. And so if you take an object and you, like this pen, and you just let it go, well, it wants to accelerate towards the nearest massive object, which happens to be the Earth, and the center of the Earth happens to be down. And so it follows a path in space-time, which is, I guess, the shortest path in space-time, causes it to accelerate downwards. And that will be true even for a beam of light. If a beam of light goes past me, its shortest path will also include an acceleration downward. Now, it's very difficult to measure that since the speed of light is so fast. You don't really see that curvature here on Earth. But if you look far enough and if there's a strong enough gravitational field, like from the sun, you can just barely measure that bending of light. So it's a very important aspect, this aspect of general relativity, that everything, even space and time, get curved by a gravitational field.
How does time get curved?
Well, so space and time are related in Einstein's theory of relativity. You've got three spatial coordinates and one time coordinate, and all of the whole universe is this four-dimensional space-time, and masses bend that four-dimensional space-time, and so they can cause, through time, things to accelerate towards each other, and that's the basic theory of gravity from relativity.
So, when you showed us the pen's got mass to it. There's something there.
Mhm.
Are you saying that a light beam has mass to it that can get attracted by gravity the same way a pen can?
Well, no, I mean, I guess light is a massless particle. Light has energy. And so in Einstein's theory, energy is a form of mass. So I guess mass is concentrated energy, and he relates energy to mass in this formula, E equals mc squared. So energy is equal to the amount of mass times the speed of light squared. But the main thing with light is that it travels along what's called a geodesic. So it just means a straight line in space-time. And so, or I guess the shortest path in space-time. And if you're near a big massive object, lots of mass, concentrated mass, like a star, for example, or a black hole or something, then those geodesics are curved. And they include an acceleration, just like that pen, an acceleration towards that massive object.
Fascinating. You
Yeah.
must love your subject.
I really do. I mean, I'm teaching physics here, and I teach a lot of big first-year courses. But yeah, I love having conversations with students after class or in office hours, and things get pretty wild. I like quantum mechanics as well, and there's a big interest in quantum computation and quantum information these days, which a lot of students are interested in that field and how it's going to affect computers. So gravity and quantum mechanics, it's all sort of intertwined and all at the cutting edge of physics research. So yeah, I love talking about that stuff.
We're going to take a break for some messages and come back in just 2 minutes and maybe talk a little bit about quantum, because I do think that there is a connection there with Jason Harlow, a really smart guy who's telling us a little bit about this total eclipse of the sun that's going to happen on Monday in the afternoon. And we're not going to see it here in Toronto or Mississauga, but I think a lot of people are planning to go down toward Hamilton, Niagara Falls, Fort Erie, etc., so they can actually experience a total eclipse of the sun. Hopefully, it's going to be a nice, clear day. Stay with us, everyone. Back in just 2 minutes. Welcome back again, everyone, to the Brian Crombie Radio Hour on Saga 960. I think a lot of us are becoming really interested in this event that's going to be happening Monday afternoon around 3:18 p.m. here in the Toronto area. We're going to have a eclipse of the sun. In Toronto, Mississauga, it's going to be a partial eclipse, but down Hamilton, Niagara Way, it's going to be a total eclipse of the sun. Our guest tonight is Jason Harlow. He's a teaching stream professor in the physics department at the University of Toronto, but he's got a PhD in astronomy and astrophysics from the Pennsylvania State University, and he's got a lifelong interest in telescopes and stargazing. This is going to be his second total eclipse of the sun. He actually traveled, 30 years ago.
I did, yeah.
30 years ago to Costa Rica so he could view a total solar eclipse. Jason, let's talk about a couple of other things. I just got to ask you, what is astrophysics versus physics?
Well, astrophysics is talking about the reasons why certain astronomical phenomena happen. My field was stellar astrophysics, so I was looking at stellar interiors, what's happening between when the nuclear fusion happens at the core of a star and how that energy gets out to the surface. Also stellar atmospheres, which is, that's that photosphere that we were talking about of the sun that's going to get blocked out on Monday. How does the atmosphere work, and how do different frequencies of light escape the atmosphere and make it to our telescopes? And then astronomy is more the observational side. What can we see from our telescopes? How can we analyze that light and learn more about the stars and about galaxies? And so astronomy and astrophysics is kind of, I guess, the theory and the experiment side of astronomy.
You said a lot of people are getting interested in quantum mechanics, quantum issues. I interviewed a gentleman last week who's got a large company that's into quantum computing in Toronto called Xanadu, and he's actually what's called a unicorn, which is a valuation of over $1 billion US as a private company. And what he was saying is that he thought quantum computing would be as big a change to us as the development of the internet was. And he said the reason why is because the difference is that regular computers use electricity and quantum computing uses light. Can you explain that?
Well, I guess I'm not an expert on this like Christian is, but it's my understanding is that quantum computing uses qubits. So a bit being a, a number that's stored in your computer somehow. It's usually with electricity, a magnetic or electric bit could be a capacitor, an electric capacitor, which is either 1 or 0. But in a quantum computer, the information is stored as these qubits, quantum bits, which are in a mixed state of both 1 and 0. And they don't become either a 1 or a 0 until they're observed. And yeah, I think you're right that usually qubits are stored as photons, and photons have a spin, and so the spin can be one direction or the other, either a 1 in one direction or a 0 in the other. And so most of the I guess these prototypes of quantum computers that are starting to be built these days use photonics and light instead of electricity in order to store these numbers. But yeah, it's pretty mind-boggling. And this idea that you can, if you have many qubits and feed them through a process, you can, in parallel, be doing all these amazing number of calculations at the exact same time, because I guess in some universe or something, all these different possibilities of ups or downs are all happening at once. And so it's a revolutionary change in how we think about computing. And these days it's pretty theoretical. I don't really know anybody who has a quantum computer, and it's something at U of T that it's mostly theoretical and not experimental. But there are some experimentalists that are working on trying to get a qubit around, and yeah, maybe in the next 30 years from now, it'll be quite a different landscape.
How did you become so interested in astronomy and astrophysics?
Well, I guess when I was really little, I watched a lot of Star Trek and made me think about going to the stars and maybe exploring things. And I was also, read a lot of National Geographic about space missions to low Earth orbit and the space shuttle. I was very interested. My grandmother and I used to watch all the space shuttle launches. But yeah, I've been interested in going to space, and I thought maybe when I was a kid that I'd be an astronaut, but that didn't happen. But yeah, just space being really that final frontier. Is we could go there. We could go to the moon, and we will go back to the moon soon. And right now, I'm very excited because NASA's working on putting the first woman on the moon, which should happen in the next 5 or 10 years. And then going beyond that, actually setting up a moon base, and then from there going all the way to Mars and trying to set up a Mars colony. I think that these are great things. It's very exciting to think that we could actually get off our planet and start exploring around what's out there.
Since you were a fan of Star Trek, I got to ask you, what is Mach 1? Or, I've always wondered, what is Mach?
Well, you mean warp, I think. So Mach
Warp.
is real. So Mach is just the speed that you're going in terms of the speed of sound. So planes can go faster than the speed of sound. Mach 1 is 340 meters per second. That's the speed of sound. So in Star Trek, they have something similar. They call it warp. So there's warp 1 and warp, and then you're going faster than the speed of light,
So warp
which
1 is the speed of light.
well, I think I'm not sure exactly how it works, but I think warp one is even greater than the speed of light. You start to warp space and time using your warp engines, and that allows you to travel faster than the speed of light. Because in real life, down here in not Star Trek world, you cannot go faster than the speed of light. It's impossible. And so, but I guess science fiction writers don't like that because it means it would take a very long time to get even to the nearest star. So they invented this warp drive idea, which would allow you to bend space and time and zip through faster than the speed of light. So, but yeah, in real life, we don't have warp drive.
If we couldn't go faster than the speed of light, how long would it take us, do you think, to get to Mars from the moon?
Oh, so Mars and the moon are here in the solar system. And so those you can get that. I think the trip to Mars takes about 9 months. So, and that's going in a kind of a minimum energy trajectory. It's possible to get to Mars even in something like 2 or 3 months. If you have enough fuel, you can just power right through there. To get to the moon takes about 2 or 3 days. So, and that's because we've been to the moon lots of times back in the 60s before I was even born. This is the last time that anyone went to the moon. Back in the late 60s, early 70s, took about 4 days to get to the moon. That's still about the amount of time it would take when we go these days. But yeah, to get to the nearest star, so going to a different star than the sun, is a whole different thing. That would take, decades, maybe at least 10 years to get to the nearest star.
So
And
smart
maybe,
people like you have got to start working on warp speed.
well, yeah. Or working on some way of living in space, deep space for a long time, or I don't know, going into hibernation in between stars or something. Like there's different ways of how we think we might be able to go to the stars, even without warp drive. Because I don't know what warp drive is. I don't think we're on the verge of discovering that.
I've heard lots of people say that things like what's happening on Monday, a total eclipse of the sun, and experiencing it can change their life, change their dreams of what they want to do and what they want to become. As a parent, if you've got a kid that's interested in science or physics or the world or space or something like that, what suggestions have you got for them?
Well, I mean, the first thing is to wear eye protection during the the partial solar eclipse. And so I have a whole family pack of eclipse glasses that I got for $25, and that's definitely hand those around so that we can safely look at the partial eclipse. But if you're down and if it's clear and it turns to a total solar eclipse when it's really dark and there's no more bright spot in the sky, yeah, I'm going to encourage my kids. I have a 12-year-old and a 10-year-old that I'm going to be encouraging to just look around, and experience it, and get off their screens and actually just feel what it's like to be out there under the stars in the day and looking at this beautiful phenomenon that's really once in a lifetime.
I saw a video on social media that I think one of your sons posted.
Yep, my
Excited
son.
about this.
Yeah, that's my 10-year-old. I got him to talk about, I guess we are thinking something like TVO Kids might pick up something about, from a kid's perspective, what's going to happen. And he mentions at the end of the video that the next time that this will happen will be in Ontario. It'll be 2106 when I'll be 93 years old. Then I'll be long dead at that point, so I don't care. But for him, it will happen twice in his lifetime, so that's good. We hope.
So it's a very rare event. It's had, as you say, lots of references in history and literature in the past. Do you think we should go see it? Like,
I
would you
I
recommend it?
I absolutely recommend it. I don't think you want to miss it. If it is quite cloudy or rainy that day, that's a different story. If you know that you're not going to see it, then I don't think it really matters too much if you're in Mississauga or if you're in Hamilton. It's going to get pretty dark at about, like I say, about 3:18 in the afternoon. You'll really notice that something weird is going on outside, even if it's cloudy. And so that's kind of a fun experience. And if you're in Hamilton, it'll get quite a lot darker, even in full cloud cover. But if it's clear, I mean, to be able to see something like that, to look up, I think it's going to be, I mean, for me anyway, who likes looking up and thinking about space, to have the sky just disappear and you see the stars beyond it, that in itself, I think is really, really inspiring. It makes you think about, what is night? What is day? And I think what I'm saying is that if you're in the path of totality or not in the path of totality on Monday, the difference is literally night and day. and which it is. You go down and it'll be night in the day. So I think it's definitely worth the drive and worth braving traffic.
The um the other thing that we talked about is that you said there's a couple of parties. Is this something that is better experienced by yourself or with other people?
Yeah, definitely with other people. You want to be with friends, you want to be in a big environment. Like I say, the reason that I knew to stop looking through the eclipse glasses was that around me, everyone simultaneously went like that. There was just an intake of breath that like, what has just happened? It's very, very different when the totality really hits and you're in that very dark shadow of the moon. And so at that point, you're kind of afraid to take off the glasses, but you gradually you take them off and you're like, well, there's no problem. It's pitch dark, like it's nighttime, and then you see the sun, and it's just like again, like what has happened to the sun? What is going on here? And then yeah, to experience that with your loved ones is pretty fun. And then like I say, when the sun comes back, that collective relief that it's over, and that deep primal anxiety we have about losing the sun, I think. And you know how our environment is keeping us alive. I think that's another thing that it reminds you of is that, you know, we're only here and alive on the surface of the earth by a happy chance. And we really shouldn't mess with our environment. Like when you think about climate change and what we're doing with pollution, I think that's something that affects me as well, is this I want this earth to basically remain the same for my son and his grandson and these kinds of things. I want to preserve this beautiful place that we have where we can go outside and breathe the air and live and feel the warmth of the sun.
The dark side of the moon. Does it ever see the sun?
Yeah, so so there's two sides to the moon. The moon is locked so that the same side of the moon always faces the Earth in its orbit around the Earth. So there's what I call it the near side of the moon and the far side of the moon as viewed from Earth. But as the moon orbits the Earth, the sun illuminates all the different parts of the moon. So if you lived on the moon, the day would be 1 month long. You'd see the sun rise, it would go over, and then it'd be night for half a month and day for the other half of the month. So despite what Pink Floyd says, there is no dark side of the moon. What there is there's a far side of the moon and the near side of the moon. But depending on the phase of the moon, the sunlight shines on all the different sides of the moon. So
Are there planets? Are there planets that don't rotate and that therefore would have half always in darkness?
well, there definitely are tidally locked planets in the universe, although I don't know, we don't know much about rotation of planets around other stars because we can't actually see them. Here in the solar system around our sun, none of the planets are tidally locked with the star, but you can imagine that could happen the same way as the moon orbited the Earth. It was these gravitational forces that caused, I guess, the slightly, you know, heavier side or the elongated axis of the moon to line up to always be pointing towards the Earth. And so it's a natural effect that could happen to a planet as well. It just hasn't happened in our solar system.
I guess what I'm driving at is to your comment about sort of the lucky chance. The rotation is pretty critical, but you know,
Yeah.
if we had half that was never exposed to the sun,
Yeah.
you know, that wouldn't be able to create life. And I don't know if the site that was the side that was exposed to the sun would ever create life either. It needs that rotation, does it not?
Absolutely, yeah. One side of every of the planet would freeze if that happened to happen. The other side would be eternally baked in sunlight. So you can imagine that this must happen to a lot of planets. Like 51 Peg B is an example where we think that planet is almost certainly tidally locked with its central star. There's no proof of that, but since it's so close to its central star, probably one side is always facing the star, always in daytime, and the other side is always in nighttime and kind of freezing. And so if life were to develop on a planet like that, it would have to do it around the terminator, right around where the sun is low on the horizon, not way overhead, but also not disappeared completely.
Why? Why couldn't it be where it's constantly in sun?
Well, it's just, I guess, a matter of the Goldilocks zone, right? Being too hot if you're on the side with the sun, and too cold if you're on the side without the sun. So there would probably be some region in between on the kind of that sunset, it's called the terminator, right? Where the sun is just on the horizon, that perhaps life could evolve, I guess, or life could live or survive there.
I think it's going to be a time to give thought to a lot of those issues on Monday as we have this very unique experience, and we have it collectively in Mexico, United States, Canada, or parts thereof of each one of them. And you're going to be driving down to Fort Erie, I understand.
I am. My destination's, yeah, Fort Erie Beach. I'm thinking if I go there. So first of all, Buffalo is right at the center of the path of totality. It goes straight over Buffalo. And so, but Fort Erie is quite close. And also the beach there faces kind of south and west, which is exactly where the sun will be. The sun will be over the south and west. And so to have a nice bunch of Lake Ontario there, or I guess, sorry, Lake Erie, to look out over Lake Erie, it should, if it's clear, it should be a nice place to see see the stars as they come out.
But you got to have protection. You got to have.
Absolutely. Definitely. Yeah. Especially for that hour and a half before the totality, you need to have eye protection so that you can look at the partial solar eclipse. Do not look at the sun. Even if it's mostly blocked out, the tiny little sliver of the sun's disk that's still there can actually really cause retinal damage. And so be very careful. Make sure that you have some eclipse glasses, proper eclipse glasses before Monday. Like I say, there's a lot of places that are passing them out. University of Toronto has some. We have McMaster University in Hamilton has got a star party where they'll have boxes of solar eclipse glasses. So make sure to get your hands on some, especially for the kids.
Jason Harlow, really appreciate you coming on our show and telling us about this total eclipse of the sun and how it excited you 30 years ago to go to Costa Rica to experience it, and how it's so close to us that we should take the chance and I think experience it as long as we have protection. It sounds like something that we tell people a lot for lots of different things, and how it really sort of connects us, I think, over the millennium to something that by chance happens, and this whole idea of the moon being the sun being 400 times larger than the moon, and the sun being 400 times farther away than the moon. So it's almost a perfect connection that the moon covers almost 100% of the sun.
That's right. It's a total coincidence. And yeah, we're very lucky to be on a planet that has that strange coincidence. So yeah, I feel lucky to be here, and I think it's worth contemplating that, isn't it?
Jason Harlow from the physics department at the University of Toronto. Really appreciate it. Thanks so much.
Thank you, Brian.
That's our show for tonight, everybody. Thank you so much for joining us. And remember, get some protection, and Monday afternoon, go check out a total eclipse of the sun. Good night, everybody.